Properties of space. Beginning then, with previous definitions of time, motion, and velocity, we can pass to the definition of space, matter, mass, gravitation, infinity, commensurability and incommensurability, negative quantity, etc. With regard to space, the first fact we come upon is that space is much too readily accepted as homogeneous. The very question of the possible heterogeneity of space never arises. If such a question ever arose, it was only in the domain of purely mathematical speculation or science fiction, and never passed into the concept of the real world, from the point of view of heterogeneous space. Even the most complex and metageometrical views assert themselves each to the exclusion of the others: spherical space, elliptical space, space determined by the density of matter and by the laws of gravitation. Finite and yet limitless space, in each case this is the whole of space, and in each case the whole of space is uniform and homogeneous. W. K. Clifford, 1845–1879, wrote in his book, Common Sense of the Exact Sciences, that the danger of asserting dogmatically that an axiom based upon the experience of a limited region holds universally, will to some extent be apparent. It may lead us to overlook, or when suggested at once reject, a possible explanation of phenomena. The hypothesis that space is not flat, and again that its geometrical character may change with the times, may or may not be destined to play a great part in the physics of the future. Yet we cannot refuse to consider them as possible explanations of physical phenomena, because they may be opposed to the popular dogmatic belief in the universality of certain geometrical axioms, a belief which has arisen from centuries of indiscriminate worship of the genius Euclid. This may have a connection with the idea of the heterogeneity of space. Of all the more recent definitions of space, the most interesting is the mollusk of Professor Einstein, because the mollusk anticipates many future discoveries. The mollusk may be able to move by itself, to expand and to contract. The mollusk can be unequal to itself and heterogeneous with itself. The mollusk is still, however, only an analogy, and a very timid example of the way in which space can and should be regarded. Behind this example, in order to make it possible, the whole arsenal of mathematics, metageometry, and new physics, with the special and general principles of relativity, are necessary. In reality, however, all this could be done much more simply, if only the possible heterogeneity of space were understood. Let's take space then, just as we took motion from the point of view of direct observation. A. The space, occupied by the house in which I live, by the room in which I am now, and by my body, is perceived by me as three-dimensional. This is certainly not a pure precept, for it has already passed through the prism of thinking. But as the three-dimensionality of the house, the room, and my body do not give rise to argument, it can be accepted. B. I look out of the window and see a portion of the sky with several stars in it. The sky is two-dimensional for me, it looks flat. My mind knows that the sky possesses depth, however my direct senses do not tell me so. On the contrary, they deny the truth of it. C. I am reflecting upon the structure of matter and on a unit such as a molecule. One molecule has no dimension for the direct senses, but by reasoning, I come to the conclusion that the space occupied by the molecule, consisting of atoms, protons, and electrons, must have 6 dimensions, 3 space dimensions and 3 time dimensions, for otherwise if the molecule did not possess the 3 time dimensions, its space dimensions would be unable to produce any impression on my senses. A great quantity of molecules produce on me the impression of matter possessing mass, only because of the 6-dimensionality of the space occupied by every molecule. Thus space is not homogeneous for me. The room is 3-dimensional, the sky 2-dimensional, and the molecule has no dimension for my own direct perception. Atoms, protons, and electrons have still less dimension, but owing to their 6-dimensionality, a multitude of molecules produces on me the impression of matter. If the molecules had no time dimensions, then matter would be emptiness for me. What has just been said must leave several points requiring explanation. First of all, if the molecule has no dimension, how can atoms, protons, and electrons have still less? Secondly, how do time dimensions affect our senses, and why would space dimensions by themselves not produce any effect on us? In order to answer these questions, we have to enlarge upon the above considerations. A star that appears to me in my two-dimensional night sky as a twinkling point actually consists of two enormous suns surrounded by a whole series of planets, and separated by colossal distances. This twinkling point therefore in reality occupies an enormous expanse of three-dimensional space. Here again the objection may be raised, just as in the case of the four kinds of motion, that I take purely subjective sensations, and attribute to them real meaning. Again, as in the case of the four kinds of motion, I reply to this that what interests me are not sensations, but the interrelation of their causes. The causes are not subjective, but depend upon definite and objective conditions, namely comparative magnitude and distance. The house and the room are three-dimensional for me, by virtue of their commensurability with my body. The sky is two-dimensional, because it is remote. The star is a point because it is so small as compared with the sky. The molecule may be six-dimensional, however, as a point, i.e. taken as a zero-dimensional body, it cannot produce any effect upon my senses. These are all facts, and there is nothing subjective in them. However, this is by no means all. The dimensions of my space depend upon the size of my body. If the size of my body could change, then the dimensions of the space around me would change also. Dimension therefore corresponds to size. If the dimensions of my world can change with a change in my size, then the size of my world can also change, but in what respect? The correct answer to this question will immediately put us onto the right track. The smaller the reference body or reference system, the smaller the world. Space is proportionate to the size of the reference body, and all measurements of space are proportionate to the measurements of the reference body. Yet it is the same space. Let's take an electron on the Sun in its relation to visible space, and to the planet Earth. For the electron, the whole of visible space will be of course only approximately a sphere 1 kilometer in diameter. The distance from the Sun to the Earth will be a few centimeters, and the Earth itself will be almost a material point. A ray of light from the Sun reaches the Earth for the electron instantaneously, which explains why we can never intercept a ray of light halfway. If now, instead of an electron we take the Earth, then for the Earth distances will necessarily be much longer than they are for us. They will be longer by exactly as many times as the Earth is bigger than the human body. This is necessarily so if only because otherwise the Earth could not feel itself the three-dimensional body we know it to be, but would be for itself some incomprehensible, six-dimensional continuum, and such a self-feeling would contradict the rightly understood principle of the unity of laws. The reason for this is that if the Earth could be for itself a six-dimensional continuum, then we also would have to be for ourselves six-dimensional continua. But since we are for ourselves three-dimensional bodies, the Earth also must be for itself a three-dimensional body. Although it should be noted at the same time, that it is not possible to assert with certainty that the Earth's concept of itself must necessarily coincide with our concept of it. If we now try to imagine what the space occupied by terrestrial objects must be for the electron on the one hand, and for the Earth on the other, we shall come to a very strange and at first glance paradoxical conclusion. Things that surround us, tables, chairs, objects of daily use, other people, etc., cannot exist for the Earth, for they are too small for it. It is impossible to conceive a chair in the planetary world. It is impossible to conceive an individual person in relation to the Earth. An individual cannot exist in relation to the Earth. The whole of humanity cannot exist by itself in relation to the Earth. It exists only together with the entire vegetable, insect, and animal kingdom, together with all that has been made by the hand of man. There can be no serious objection to this, because a particle of matter that is as small in relation to the human body as the human body, or even all of humanity, is in relation to the Earth, certainly cannot exist for us. It is quite obvious that a chair cannot exist in the planetary world, because quite simply it is just too small. What is strange and what is paradoxical, is the inference that a chair cannot exist for the electron or in the world of electrons also, and also because it is too small. This is an absurdity. Logically it ought to be that a chair cannot exist for the electron, because a chair is too big compared with the electron. But it would be so only in a logical, that is, in a three-dimensional universe with a permanent space. The six-dimensional universe is illogical, and the space in it can contrast and expand on an incredibly large scale, preserving only one permanent property, namely angles. Therefore, the space existing for the electron, which is proportionate to its size, will be so small that a chair will occupy practically no room in this space. Thus we have come to a space that expands and contracts with the size of its reference body, an expandable and contractible space. Einstein's mollusk is the nearest approximation to this idea in new physics, but like most of the ideas of new physics, the mollusk is not so much a formulation of something new as an attempt to show that the old will suffice. The old in this case is immovable and unchanging space. The same can be said of the general idea of the space-time continuum. New physics recognizes that space cannot be examined apart from time, and that time cannot be examined apart from space. But what actually constitutes the essence of the relation of space to time, and why phenomena of space and phenomena of time appear to be different for direct perception, new physics does not explain. The new model of the universe establishes exactly the unity of space and time, and the difference between them. It establishes also the principle that space can pass into time, and time into space. In old physics, space is always space and time is always time. In new physics the two categories make one, space-time. In the new model of the universe the phenomena of one category can pass into the phenomena of the other category and vice versa. When the word space, space concepts, and space dimensions are spoken of, what is meant by this is space for us. For the electron, and probably even for bodies much larger than the electron, our space is time. The six-point star of David that represented the world in ancient symbolism, is in reality the representation of space-time or the period of dimensions, i.e. of the three space dimensions and the three time dimensions in perfect union, where every point of space includes the whole of time, and every moment of time includes the whole of space. When everything is everywhere and always. However, this state of six-dimensional space is incomprehensible and inaccessible to us, for our sense organs and our mind enables us to establish a connection only with the material world, that is with a world of certain definite limitations in relation to higher space.